So today we're going to cover the second day of our 6.3 notes, and today we're going to focus more on graphing exponential functions. As we did introduce in the first day of our notes, when we graph exponential functions, the shape they make is a curve, so it's not a straight line anymore. So what we're going to do today is we're going to graph a few different exponential functions and try to generalize what they look like. So as a good review from yesterday as well, we know that when we look at an exponential equation, there's an a value and there's a b value. So our a value is always the number that's before the parentheses or before the thing that's getting the exponent. And we know the a value of our equation here then is 3. From yesterday, we learned that if we were making tables of this equation, the a value is the value of y. So in other words, it's the y value if the x value is equal to 0. So for instance, if I was trying to make a table of this, I know that when the x value is equal to 0, the y value must be 3. Now, by definition, if x is 0 and y is 3 on a graph, that is the y-intercept. So if we're trying to make a graph of this, I'm just going to go ahead and place the y-intercept of 0, 3. I'm going to scale by 1, so here's 0, 0, so 1, 2, 3. So there's my y-intercept. Now, to create the other values in the table, what we learned yesterday is we look towards our b value. The b value is the number that's receiving the exponent, right? And I can start to see why they chose b to represent the word base, because the base is what has the exponent. So in this case, the b value of this equation is 2. And what we realized yesterday, or in 6.1 notes, the b value in a table is what we call our constant multiplier. So, for instance, what that means is if x changes by 1, increases by 1, then that's what I would multiply the y values by. So we can go look at our table here and realize that if the x's increase by 1, I should multiply the y's by 2. So here, if the x's increase by 1, I should multiply the y's by 2. So then we also have to fill in the rest of the table, and there's a few different ways we're going to do that today. So if I'm trying to figure out what did I multiply by 2 to get to 3. So I know in my head that's 3 halves. I could check that, right? If I took 3 halves and multiplied it by 2, I would get 3. So going backwards, what was here? Now, if I can't do that math in my head, we could always use division, right? So I was starting at some number and I had to multiply it by 2, and then I ended up at 3 halves. So to undo multiplying by 2, I would take 3 halves and divide it by 2, right? If I divided both sides by 2. So I know that instead of dividing by 2, I would just multiply by the reciprocal. So that is 3 over 4. So that's one way you can find missing values in the table, just by using your patterns. We'll go over other methods in other examples. So now we have enough information to graph it. So at 1, the y value is 6. At 2, the y value is 12. And then with these fractions and decimals, we'll have to estimate a little bit. So at -1, I know that's 1.5. So at -1, we'll do 1.5. And then at -2, we have 3/4. Now, another way, or I guess what I would have you do here, is fill in the general shape just like I do. Now, when you're filling in this general shape, you'll notice that when I connect them, I am not touching the x-axis. So that right there is kind of our first general graph of an exponential function. So what I want to then finish with our notes here is, based on that b value, the b value will help us look at the graph and figure out what type of curve it has. We're going to eventually call them an exponential growth or an exponential decay. But just by looking at the b value and stuff, we want to think about being curved up or being curved down. And there's a few other more intricacies to that, like when we change our a value, but we'll get to that at the end. But in general, I just want to know that the b value helps us think if it's rising or falling. So this is our exponential curve. And we look at a graph here, we just have some nice reminders for ourselves. The domain, right? If I thought about figuring out what is all the x values on my graph, well, if the x values go left forever and then they go right forever, my domain would be all the real numbers. Or if I think about the equation, the domain values are all the x's we are able to use. So what number can I use for an exponent? Are there any rules on what I could plug in for x? And I can do 2 to any power. So there's no rules on the x's. What we notice here about our range value, though, or in other words, the y values, I notice that my graph never goes below the x-axis. and it actually never touches it. So what I realize is that every single point on my graph will have a y value that is greater than 0, and it never will be 0. So that's our first graph there. So let's keep moving forward. So here, what we're looking at is just looking, again, we've changed a few things. So let's keep graphing. So in this case, we have a new equation. So our a value, the number out front, we can see that's a 6. So in the table, that's going to be our y value when x is equal to 0. So down here, when x is equal to 0, we can fill in our y value of 6. On the graph, we already know that's our y-intercept. So I'm just going to fill that in right away. So 0, 1, 2, 3, 4, 5, and 6. So there's our y-intercept. Now we go to our b value to help us get more values in our table. So we know b is the number that has the exponent. So in this case, our base is 1/2. And we know that that 1/2 is the constant multiplier. And what that means, if we increase x by 1, that's what we should multiply the y values by. So here I can see that, yes, I increased x by 1, so I'd multiply this by 1/2. So 1/2 of 6 is equal to 3. Here, if I increase x by 1, I should multiply my y values by 1/2. So 3 times 1/2 is 3/2. If I increase x by 1, then I should take this and multiply it by 1/2. So 3/2 times 1/2 is equal to 3/4. Now, when I'm looking for this one, again, we did look at some ways that we could use guess and check. Like I'm thinking about what number started here, so I multiplied it by 1/2 to get to 6. Well, that must be a 12. But another way that you can do it is we have an equation, so feel free just to use the equation and plug in the x value. If I know x is 1, I can use my equation, y equals 6 times 1/2 to the -1. So I know what a negative exponent means. A negative exponent, so I'm just going to rewrite that. So the top would get the negative exponent and the bottom would get the negative exponent because we have a fraction inside of a parentheses. So if each of them has a negative exponent, we would flip both of them. And then I know 6 times 2 is equal to 12. So another way that you can find table values is just to simply evaluate the equation using your rules of exponents. So we go graph this one now. So at -1, we're at 12. And then at 1, we're at 3. And then 1.5. And then 3/4. And just to kind of demonstrate, if I did another one, 1/2 of 3/4 would be 3/8. And then 1/2 of 3/8 would be 3/16. So this number is going to keep getting smaller and smaller and smaller. But what I would ask you, if I keep taking half, like if I start with a square here and I cut it in half, I have a smaller square. If I cut that square in half, I have a smaller square. If I cut that in half, even smaller and even smaller. If I keep cutting something in half, I'm never going to get to 0 though. I always have something left. Maybe it's a really small piece, but it's going to be something left. So again, just like we saw before, when I'm drawing the rest of this graph, the numbers are so small, so I can't really do it. So I'm going to make sure that it just looks like it's following the x-axis without actually touching it. So here's our next one. What we can see here is that this one now looks like it's going down, right? So we can see our b value, which was now 1/2, made the graph look like this. Whereas if our b value was 2, it made the graph look like this. So again, with this one, I think about the domain. Now remember, the domain is just the x values. So if this was measuring the x values on my graph, if I keep sliding this, all these x values are on the graph, but since there's an arrow, every single x value is going to be on my graph. Or in other words, what can I put as an exponent? There's no rules on the numbers that I can use as exponents. So the domain of this graph is, again, all real numbers. Now when I look at the y values here, if I was thinking about what y values are on my graph, I'm just going to use a little horizontal line to describe that. Since this has an arrow, I would just keep going up and up and up and up and up. So the y values are going to get bigger and bigger and bigger and bigger. But here, what I'm noticing, if I keep following the y values, they're going to get really close to the x-axis, but never actually be the x-axis. So in other words, like a little dotted line here, it's never going to touch this line. And that's the y value of 0. So every single y value on my graph is going to be greater than 0. So another example that we have, we can see our a value is now -4. And we know that the a value of -4, that is our y value in the table when x is equal to 0. Or in other words, it's the y-intercept on our graph. So let's plug that in. So here we have -4. And then our graph will have a y-intercept of -4. looks like I need to flip this over. You might just have to make your own graph. This one looks like it's a little too positive. Well, we'll just estimate, so we can just use what's there. So 0, -4. And then what we know is we would then move to our b value. So our b value in this equation is going to be 2. And we know that the b value is just our constant multiplier. So in other words, if we increase x by 1, we should be multiplying by 2. So here, if I increase x by 1, I should be multiplying by 2. So here we might need to estimate a little bit. So like -8. Let's just put that here. And then if I increase x by 1, I would need to multiply again by 2. So that brings me to -16. And again, for that one, we'll just have to estimate because I didn't provide a proper graph. So let's just put that way down here. Let's go backwards though. So I'm thinking about what number was here that if I multiplied it by 2, I would have gotten -4. Well, that must have been -8. And I hope here that we're realizing if I'm going backwards through the table, instead of multiplying by 2, I'm just dividing by 2. And here, I'm sorry, I meant -2. So if I'm going backwards, I'm really dividing by 2. So -2 divided by 2 must have been -1. Or in other words, if I checked it, if I was here and I increased x by 1, I would have multiplied by 2. So then here, that must have been -1/2. Or again, we could just use our equation. So if we have this equation, the x value is -3. So y equals -4 times 2 to the -3rd. So we know in our order of operations that we need to do exponents first. So 2 to the -3rd is 1 over 2 to the 3rd. And we know that 2 to the 3rd is 8. So we get -4 over 8, which is -1/2. So if x was -3, we get -1/2. So for the last one, I will plug it into the table. So if I'm trying to find the value of y when x is -4, we'd put in -4 for the x value. And then we'd simplify. So we know that 2 to the -4th, that really means 1 over 2 to the 4th. And I know 2 to the 4th is 16. So -4 divided by 16 is -1/4. And I can check, if I started there and increased x by 1, I would have multiplied by 2. So as we graph this, we'll have to approximate some of these decimals. So at -1, we're at -2. At -2, we're at -1. Then we're at 1/2. Then we're at 1/4. Then it'd be 1/8, and so on and so forth. So again, you can see I'm going to be getting really close to that x-axis, but I'll never be able to get to 0. If I keep taking like something and dividing it by 2, I always have something left, even though it's really small. So with this curve, we'll see that general shape again, but now it's kind of going a different direction. So here, if I think about the x's, this arrow means we're going left forever. This arrow is tending right forever. So every single x value is on the graph. And again, if we think about the equation, what number can I plug in for an exponent? There's any number that I could choose. So I could plug in x as anything, so all real numbers. Now for the y values, what we notice here is that it's kind of flipped over from the other ones. So all the y values are negative, meaning that the y values are all less than 0. They're never going to touch that y value of 0. Last one for today, we can see our a value of this one is -6. And we know that in a table, that is our y value when x is equal to 0. So in other words, on the graph, that's our y-intercept. So when x is equal to 0, we can plug in -6. Our b value, right? B stands for base, so the thing that's getting the exponent is 1/3. So our base is 1/3, and we know that this is the constant multiplier. And that means that's what we'd multiply y by if we increased x by 1. So we can do that a few times. So like here, if I increase x by 1, I should multiply this by 1/3. So -6 divided by 3 is -2. If I increase x by 1, I'd have to multiply this by 1/3. So that gives me -2/3. If I increase x by 1, I'd have to multiply by 1/3. And I know that -2/3 times 1/3 is simply -2/9. Now going backwards, again, we can use the pattern. Instead of multiplying by 1/3, Going up, we'd be dividing by 1/3. And we know that if I took a number like -6 and divided it by 1/3, we'd actually multiply by the reciprocal. So I would get -18. For the last one, we can just use the equation as well. If we know our equation is y equals -6 times 1/3 to the x, if I plug in x is equal to -2, well, I know that means that since I have a fraction inside a set of parentheses, both numbers would get that negative exponent. So that means both numbers would flip over. And I know -6 times 9 is -54. And again, I can check, right? If I started there and followed the pattern, if I increase x by 1, I should multiply by 1/3. And 1/3 of 54 is 18. If I increase x by 1, I should multiply by 1/3, and 1/3 of 18 is 6. So when we graph this one, we'll have to, again, approximate some answers. And what I'm going to do is, I'll just approximate the answers. The graph isn't super great. I'm sorry about that. But at -2, we're at -54. 0, 6, 1, 2. So what we can do for our graph here, since I didn't really give you a good one, is we can just kind of approximate. So at -2, we're supposed to be way down here at -54. At -1, we're at -18. And then at 0, we're at -6. So there's 0, so we can just kind of place 1 somewhere in there. And then at 1, we're supposed to be at -2. At 2, we're at -2/3, -2/9. Now it's getting really hard, so we can just kind of approximate. And again, what we're going to notice is we will never touch that x-axis, because if I keep just cutting something into 3 pieces, there's still a size of that piece. Even though it gets smaller and smaller and smaller, I can always take 1/3 of something. So we see here again is that we have all the x values, so we have all real numbers, and that's pretty much true for our exponential functions. We know that x is just the exponent, and we can raise a number to any exponent. And again, what we see similarly here is that our y values are all negative, and they get really, really close to that, but they never actually touch the x-axis, and that's when y is equal to 0. So all the y values in our function, or all the outputs we'd get, would be less than 0. So summarizing, what we realize is the values of a and b can determine what the graph will look like. So here, if our b value is greater than 1, we know that our graph could look like this. If our b value is less than 1, but bigger than 0, because we don't have a negative base right now, it would look like this. And the knowledge that we want you to summarize and start to kind of memorize in this core concept is if you saw something like this, like 3 times 6 to the x, what you would want to do is just be able to generalize and say, what would this look like? So if my b value is bigger than 1, it's something like this, right? We're going to call that growing. Am I getting more and more positive or getting more and more negative? So it just depends on what a is. If a is positive, then it would look like the blue one. And here, since a is positive, I know that this graph would look something like that. More specifically, I would even know the y-intercept would be 3. If you saw another example, like an equation that looked like this, like -6 times 1/5 to the x, what I can start to memorize is my b value is between 0 and 1, and my a value is less than 0. So it would look something like this. So you can start to generalize so that before you make a table, you know what it should look like. So that's the summary of our graphs today. And the last part of our notes is just bringing some formal language. What we saw above is that all those exponential curves will never touch the x-axis. And we know the x-axis is really the line y equals 0. So in other words, exponential functions will get really, really, really close to the y value of 0, but they will never touch it. So then I just have like a definition that I'm going to write in here that I would ask you to copy. And this is what we mean in formal math language. That's called an asymptote. And an asymptote is just a value that a function, like an exponential function, would approach, meaning it gets closer and closer and closer to, but never actually touches. And there can be asymptotes at x values or y values or other lines or something like that, but you just need to know what an asymptote is. So on a graph, what you'll notice is that we usually put in an asymptote as a dotted line. That's why I put in all those dotted lines here. They're not actually part of the graph. We're just trying trying to indicate to our reader who's looking at the graph that this curve gets really close to the x-axis but never actually touches it. So that's why I've been using a dotted line to indicate an asymptote. So when you graph exponential functions, I would graph the asymptote as a dotted line.